So in our previous video, we have seen this network, short circuit current contribution, source grid was there, two winding transformer was there. So we created a short circuit, three-phase short circuit fault here and single line to ground fault here, and we have seen what was the value for three-phase short circuit current, 14.123 kiloamps, and manually we calculated here 14.168, almost matching, and single line to ground fault it is 14.322, and in ETAP single line to ground fault 14.291, 14.322, so almost matching. So now today what we will try to cover, we will take this branch, we will close this breaker, and we will see what is the fault current contribution from this source side as well as from by this load side. Today's video will cover the fault current contribution from this 5 megawatt motor which is connected through a cable. This current contribution plus source side current contribution. So let's start today's video discussion, which is, let's name is case 2. Case 2 with motor load. Okay, so for this we will take first the motor parameters. We'll try to find out what are the motor parameters inputs. As we can see, the motor rating is 5000 kilowatt or 5 megawatt. So rating 5000 kilowatt. Then what is X by R ratio? This is input. How to find out? So this is 5000 kilowatt motor, and X by R ratio, which is 10.825. Unitless. What is power factor? Motor power factor, full load power factor, it is 95%. So power factor is 0.95. Next is efficiency. Motor efficiency 100%. Full load current efficiency is 90%. So efficiency is 0.9. Next we need to mention reactance value. How to get it? This is the value of X double dash 15.319. 15.319, that is in percentage, right? This is in percentage. Okay, so that is in point. If it is in per unit value, so this divided by 100. This is per unit value. 0.15319. So from this motor rating, efficiency and power factor, we can find out motor full load current, IFLC. Full load current, we know the formula, equals to kilowatt rating divided by root 3 multiplied by voltage is 11 kV. We are taking this voltage 11 kV. Power factor into efficiency. So 306, this is in ampere. So what is MVA, motor MVA? That is equals to root 3 into voltage into full load current. Root 3 into root 3 into voltage. Voltage is 11 kV into current, full load current. So 5847. This is in kVA. Sorry. MVA. This is motor MVA base. So we have got this X dash per unit. What is the value of R dash per unit? This is equals to X dash per unit divided by X by R. So we know the motor X by R value. So R dash per unit equals to this X dash per unit divided by X by R. So this is coming, yeah, X by R. This is in PU. Yeah. So we know now this is, so now for motor we have got X dash per unit value. and R dash per unit value. Okay, now if you can see, this is the motor MVA, this is motor MVA, and we need to change the base corresponding to this base MVA, 100 MVA base. So we need to change in motor base. So RM or motor PU new, what is this value? That is equals to this R value into new MVA, which is 100 MVA, divided by motor MVA, which is this one, but this is in kVA. That means we need to multiply by 1000. So 0.2411. This value is in PU, per unit value, and in the same way, just copy and paste this is motor reactance value XM PU, which is equals to, let's correct it, so it will be 66 B66, means this reactance value multiplied by new MVA, which is 2 B2, divided by motor kVA, means 68. Yeah, so 2.61 per unit. This is in yellow. So this is now corrected, changed in motor base. Sorry, this is converted into the new MVA base. So we'll consider for this motor, this is the resistance value and this is the reactance value. Just like what we got for the grid, for the source grid, this is the resistance value and this is reactance value. For the transformer, we change the base and again multiplied by transformer impedance correction factor KT. So this was the corrected value, corrected R value and corrected X value. Similarly, here also for motor, this is changed R value, resistance value and reactance value. So we are done for the motor part. Now we will see the cable part. So cable parameter. So now for cable, what are the parameters we need? First of all, resistance value R. Where to get this? Go to impedance tab. Here this is R value 0.098. So 0.098. This is in ohm. This is in ohm, right? This R value, this is in ohm. Next is the reactance value X value also 0.09 ohm, 0.09 ohm. So R and X value. Now we need to correct this R value, it's R dash, using the formula, means temperature correction formula. What is that temperature correction formula? We are using the copper cable here. We are using copper cable, and this is XLPE cable. So what is the corrected impedance, corrected resistance will be the old value of resistance into 234. This is copper, so 234.5 plus TC. TC means the conductor temperature, which is 20 degrees centigrade. TC divided by 234.5 plus TB. What is that? Where this TC is TC TC equals to 20 degree centigrade, 20 degree TC equals to 20 degree centigrade, and TB equals to 90 degree centigrade, 90 degree centigrade, because this is XLPE cable, So if it is PVC cable, it will be 70 degree centigrade, but cable conductor temperature is always mentioned in 20 degree centigrade. So we need to convert this cable resistance value here, like R dash equals to this old R multiplied by 234.5 plus 20 divided by 234.5 plus 90, so 0.0768. Again, this is in ohm, so this is the R dash value. Now we need to calculate this R value, this R dash value and this X value in per unit, because we are doing the manual calculation using per unit value, but this unit is in ohm, right? So for this we need to calculate the base impedance. What is base impedance? ZB. What is ZB? ZB equals to base kV square by base MVA, right? Base kV square by base MVA. So what is base kV? Base kV is 11 kV, because this is 11 kV system. We are calculating the fault current here at 11 kV. So this is equals to base kV 11 kV square divided by base MVA. Base MVA, what is that? That base MVA means 100. We are calculating based on the new MVA base is 100, so it is 1.21. That is also in ohm. So now we can find out the resistance value and reactance value in per unit. So R pu equals to, what is that? R dash by R dash equals to R dash divided by base impedance. This is 0.06, 0.063. This is in per unit. Now this is in pu. The same way, reactance value in per unit equals to the reactance X value divided by this base impedance, what is 0.07. It is in pu. So for cable, these are the values. We have got R value and X value, and for motor, this is the resistance value and reactance value. Okay. Now we need to calculate the equivalent Thevenin equivalent impedance as seen from this fault location, because we have created the fault at 11 kV bus. And if you see the source grid side, means grid and transformer, those two are in series. Also here this motor and cable, these two impedances are in series, but these two networks, these two branches, basically these two branches are in parallel, because we are creating the fault here at 11 kV side. So these two impedances will be in series, and these two impedances will be in series, but these two branch impedances will be in parallel. That means the equivalent impedance will be this impedance in parallel with this impedance, right? So first of all, we will calculate what is the series impedance considering this motor and connected cable. So what is the R RPU? RPU equal to this motor R value plus cable. This is in per unit. Similarly for X per unit value, this will be this X per unit of motor plus X per unit of cable. It's absolutely fine. So these two values we need to consider. Now if you see, this is for the motor and cable series resistance value and series reactance value. And previously we have found out the R value here. This is R1 and X1. R1 and X1 value means, I think this was the for this transformer and source grid value. So we can consider these two value for the first part, means for this part, and for this branch circuit we have calculated this. Let's mark it in different color. Yeah, these two values we need to consider, because this impedance value is in parallel combination with this value. So what will be the new equivalent value? That will be the resistance value, this resistance value in parallel with this resistance value, right? So this value will be equals to this into this divided by again this plus this. What I have done, I have paralleled this, and I have found out the equivalent resistance value, right? Similarly, R pu new, that is equals to this X value into this divided by X value plus this. So this is also in PU. So this is the final one. This is the final R value and X value in per unit for this fault location at 11 kV system. This is the Thevenin equivalent impedance, this branch and this branch, right? So it is coming, our PU is this and XPU is this, right? So what will be the value of Z? What will be the value of Z1? Value of Z1 is equals to square root of this square plus x square this is in per unit. So point Z1 equals to, what is that value? Z1 equals to 0.3540 watt. And what is Z2 value? Z2 equals to same Z1. Z1 equals to Z2 means positive sequence impedance equals to negative sequence impedance. But for Z0, we need to find out the Z0 values. Okay, for Z0, here in the previous video what you have done, since this is delta star connected solidly grounded system, so Z0 value will not consider the source impedance because the primary side of the transformer is delta connected, right? So in the same way, here also, to calculate the Z0 value, we have to consider this cable and motor resistance reactance value, there is no doubt. But for here, we have to consider separate value for this, because we have source parameter, means we have considered for this Z1 source impedance also, but here for Z0, only the transformer resistance and reactance value, right? So let's find out the Z0 value here. What will be the Z0 value? So this is equals to, no, before that we need to find out R. If we consider R0 and X0 in this way, right? So this equals to this R value plus here only the transformer resistance value. Why? Because the transformer is delta star connected and solidly grounded system, as I explained. And here the X value will be this X value plus only this transformer reactance, not the source, not the grid reactance or not the grid resistance. This is in PU. So what will be the Z0 value? Sorry, I made a mistake. This is not in series. This should not be in series. Actually, this should be, I think, parallel. This is the parallel connection. This is not in series. So this is B83, same thing. B83 multiplied by B35, right? Yes. And here also because this should be in parallel, so B84 multiplied by B36 divided by this. Yeah, and now we can find out the value of Z equals to just square root of this square plus this square, this one. Yes, now we are done per unit. Okay, so now we know Z1, Z2 and Z0 values. So the Thevenin equivalent behind this fault location we have calculated. Now we will find out the three-phase fault current. Three-phase fault current. Three-phase fault current. And single-phase fault current. So for three-phase fault current, what is the per unit current? IEF PU, that is equals to V by Z1. So V means 1 per unit. Similarly, what we have done in previous video, equals to 1 per unit divided by Z1, so which is 2.824, but this is in per unit value, right? Next, what we calculated, the base current. The base current IB. What was the base current? Base current means base MVA divided by root 3 into base kV. So base MVA, now base MVA we know 100 MVA divided by root 3 into base kV. Root 3 into base kV. kV means 11 kV. So 5.24. 5.24. Sorry, this is not PU. This is in kiloampere. This is in kiloamps. This is the base current. So what is the actual current? So 5.24 is the base current and 2.824 is the per unit current. So what is the fault current? Actual IF actual equals to this multiplied by per unit value multiplied by base current. This 14.82. This is in kiloamps, right? This is in kiloamps, 14.82. Now let's go back to ETAP generated output. So we will simulate this. This is in network. This is also connected motor. So let's calculate what's the fault current here. This is 15.712. This is 15.712. No, this is single line to ground fault. What is the three-phase fault? 16.313. So 16.313, but here it is coming 14.82. Why? Because we have also done in our previous video, we need to consider this C factor as 1.1. So we need to multiply with this C factor. The same thing equals to 1.1 multiplied by this value. So this is in kiloamps. So this is the value we have got, 16.305. 16.305 here 16.313, it is almost matching with the ETAP software, right? This is 16.313, this is 16.305, so it is almost matching, right? Now let's calculate the single the SLG fault also. So SLG fault, SLG fault current calculation. Yeah, so what will be the per unit current? The per unit current will be the same thing what we have done in the previous video. What was there here? If you can see this I0, this I naught equals 3V by Z1 plus Z2 plus Z0. So 3V, 3V means 1 per unit. So 3 into 1 means 3. 3 divided by Z1, right, plus, sorry, equals to 3 divided by Z1 plus Z2 plus Z0. So this is this 2.85 per unit. This is in PU. Now what is base current? The same thing, that is equals to base MVA divided by root 3 into kV. Base kV means 11 kV. So this is in KA. So this is the fault current per unit value. This is, and this is the base current. So what is actual fault current? Equals to per unit value multiplied by this base current. So this is in kiloamps, so 14.28 kiloamps, and with C factor, we consider C factor as 1.1, just multiplied by this actual current, so 15.7 15.709 kiloamps. Let's go back to ETAP just to check this value whether it is matching or not. So this is 16.3. I think this is 3-phase current. If we plot single line to ground fault current, this is coming 15.712 kiloampere, 15.709, so almost matching. 15.709 or 15.712, so it is almost matching. This is the single line to ground fault current contribution, and this is 3-phase fault contribution, right? So yeah, so what we have seen for this source fault current contribution and from the load means motor connected contribution. So after this, in this video, in the next video, we will cover this lump load also. If there is any number of lump loads connected with this 11 kV system, apart from this load, apart from this motor load, if there are some lump load, so we'll see that lump load also, what is the pole current contribution, along with the source grid, along with the motor contribution, what will be the pole current contribution by this lump load if the fault is created at 11 kV bus. So in this video, up to this, we will see in the next video.